Thank you, Brian. It's impressive to see how the observability tools can help to dramatically improve AI performance. When more applications are moving into a hosting environment like cloud, a common problem is that application performance may be affected by the hosting infrastructure itself. The last speaker today is Pavel Paulau from Facebook. He will share a multi-year journey how our multi-tenant infrastructure provides resource guarantee for applications. Let's welcome Pavel.
Hi, my name is Pavel, and I'm a software engineer at Facebook based out of Menlo Park. I spent the last year somewhere between 15 different states, working remotely or just taking a break. But right now, I'm back home in the Bay Area, and I'm very excited to talk about how we provide resource guarantees in a multi-tenant infrastructure. Facebook's infrastructure consists of large services and backends that serve user requests and process different types of data safely, reliably, and efficiently. At the same time, a great number of smaller applications and services run on every host alongside these primary services. These smaller applications satisfy a diverse set of requirements, including package updates, system monitoring, network optimization, privacy checks, and other necessary infrastructure services. We refer to these smaller applications as widely distributed binaries. Some of these binaries are workload dependent. They receive requests or manage traffic directly from primary services. However, the majority of these secondary services operate fully independently. In the past, we have made a deliberate choice to avoid strict boundaries between primary services and infrastructure software. The separating model was quite flexible, allowing the entire ecosystem to grow at a fast pace. Not surprisingly, the number of widely distributed binaries was increasing dramatically, with new services, scripts, and features linking in production on a regular basis. At the same time, capacity crunch became a real problem, and we no longer could maintain this unbound growth by adding additional hardware resources. Resource contention due to unsafe interaction between primary services and infrastructure software leads to an increased application latency, correctness issues, and other instabilities. For Facebook, that means a bad user experience or revenue impacts, in addition to operational load for our production engineers. Our service owners needed guidance on how much of the available hardware resources they can safely use without risking resource contention or oversubscription. I joined Facebook about 3 years ago when many of these problems had grown intolerable. I was very excited about performance and scalability challenges, and I started working with other engineers on solving this interesting problem. Currently, we have a comprehensive and reliable solution which, to a large extent, provides sufficient resource guarantees for our services. Our solution is not based on hard resource limits. Instead, we rely on accurate resource accounting, regression prevention and detection, adaptive resource control mechanisms, and isolation techniques based on job scheduling and load balancing algorithms. This set of methodologies and tools allows us to define service-level objectives for resource usage by infrastructure software. And it's been quite a journey to get to this state. So today I'm going to talk about each of these components, design decisions that we made, problems we run into, and also how we expect this platform to evolve in the future. I won't have enough time to cover all the interesting details and aspects of the solution, so for additional details, please see our blog post at Systems at Scale website. When we started working on this problem, there were observations and indications that widely distributed binaries constitute a significant portion of the global capacity. At the same time, the exact resource usage requirement of infrastructure software was not available. Our very first step was to look at this problem holistically, choose the right data source, and provide aggregate metrics for resource usage. 3 acceptable options were available back then. An option we knew that is unlikely to work, an option we hoped we could use in the future, and an option we had to settle with. CPU and memory profiling was enabled on almost every host at Facebook, but these profiles were accurate enough only for large services. Samples obtained for smaller applications and periodic tasks were very scarce and inconsistent. Not to mention that global CPU profiling was not available for non-C++ services written in Python, Go, or Rust. And lastly, heap profiling was not enabled for the majority of widely distributed binaries. Stats collection using C-group hierarchy and counters was also available. The data was very promising, but we had some critical constraints as well. There was no visibility into individual cron tasks, smaller shell scripts, and stats collectors. The data pipeline was also limited in terms of batch processing and aggregation capabilities. We expected this option to become more feasible in the future, but we had to start with something else. A new profiling infrastructure based on thread stats and process stats was introduced around that time, provided enough CPU and memory counters for each thread and process across the entire fleet at Facebook. We could understand the impact of each long-running and short-lived process, and there were sufficient capabilities for data processing and visualization. So this data satisfied our most critical requirements at the moment, and we started building our solution around it. The next step for us was to build data pipelines for aggregation of raw host-level measurements. However, this is not straightforward. As I mentioned earlier, several widely distributed binaries are workload dependent. In addition to that, some host management and monitoring services are also hardware dependent. As a result, performance characteristics of those services can be affected significantly by hosts they run on. Also, daily and weekly patterns in resource usage were quite common as well. We very often assume that counters provided by the Linux kernel and hardware are accurate and reliable. However, at our scale, there is always a non-zero probability that a small group of otherwise healthy hosts will produce statistics that are invalid or unexpected. This problem requires more sophisticated normalization and filtering operators that should be applied to terabytes of unsampled data on a daily basis. We managed to build this pipeline after multiple iterations and several months of hard work. We knew the exact amount of CPU and memory resources consumed by each infrastructure service. In addition to that, we also provided dashboards that us engineers could use to examine this new data. With this new data, we started monitoring each process for resource usage regressions using our automation for time series analysis. This analysis is more reliable when it's applied to subsets of the fleet. Each top-level signal is usually broken down in more granular time series that represent different workloads, different hardware types, or even data centers. This analysis is typically applied to a moving time window that can vary from several days to several weeks. Using STL method of time series analysis with additional validation, filtering, and smoothing operators, we are able to establish when a given piece of software has regressed beyond its expected resource usage bounds. We detect these changes reliably on the order of 15 megabytes of memory, or 0.03% of host CPU usage. Automation is effective for both rapid increases and gradual increases over time, no matter how complex or noisy time series are. Detected regressions then get correlated with package updates, configuration changes, fine-grained profiling data, or changes in API usage patterns. Thousands of changes can take place on a daily basis, and this triage process is usually automated. This way, we can identify the root cause within a few minutes or a few hours. Of course, our environment can be quite complex, and some of these regressions are never resolved fully. We rely on future changes and optimizations to recover these lost CPU and memory resources. Our regression detection based on analysis of historical time series was not always sufficient. Even fully automated detection and triage process still require a certain amount of time. In the meantime, multiple services remain affected by ongoing regressions. And while configuration changes can be applied and recovered faster, changes to application code and package updates may require several days of testing and rollout. We decided to create a new set of canary environments to prevent these issues from happening in the first place. All updates to infrastructure services, including application code or relevant configuration, now get run through this canary testing. A canary test, or an experiment, consists of a group of test hosts and a control hosts. Each group has about 80 hosts or servers. During each experiment, we temporarily increase the sampling rate of our stats collection so that we can generate tens of thousands of samples and use the samples to compare test and control applications. These A/B tests allow us to identify if there is a statistically significant difference between test and control application. And again, we do it reliably on the order of 15 megabytes of memory or 0.03% of host CPU usage. Currently, we maintain multiple isolated canary environments to test new package updates for widely distributed binaries, new builds of the Linux kernel, or a combination of both. As somewhat expected, we began to run into limitations of our previously introduced resource accounting model. Although we could estimate the impact of each individual service, we could not understand the total overhead by summing up individual process-level metrics. In general, our approach and our model was very flat and naive, and at the same time, it was quite common for services to create sub-processes and sidecars, and it was very hard for us to reflect combined costs of these complex hierarchies. And also, process metrics, especially for memory, lack some important allocations and buffers, and this way we had more gaps in our accounting model. Resource accounting using cgroups hierarchy and counters was more comprehensive and accurate, and we decided that it was the right time for us to switch to a new model. This hierarchy not only represents the relationship between different services, but it also allows to track both combined and individual costs effectively. We started by rebuilding our profiling infrastructure. So now unsampled data is stored in databases that support ad hoc analysis and real-time data processing. We also defined individual services and slices for each relevant group of processes that run in our fleet. We also migrated cron tasks to systemd timers. Interestingly, the owners of cron tasks appreciated new features of systemd, and in general, this migration went very well and was received positively. At some point, we also tried to run smaller stats collectors inside cgroups. Unfortunately, the cost of running hundreds lightweight, short-lived processes in cgroups was too big, and we had to delay our migration. Right now, we're testing a new approach that should mitigate some of these problems and minimize this overhead. While cgroups provide accurate statistics for CPU usage, memory accounting can be tricky. Memory usage usually breaks down into anonymous memory, kernel slab, file cache, and other smaller allocations. Accurate accounting for kernel and file cache is extremely important if we want to understand the total memory usage requirement for widely distributed binaries. However, the Linux kernel can be very slow at releasing file cache and other kernel data structures when the host is not under heavy load. To mitigate this problem and understand the total footprint of each service, we rely on a utility called SendPy. SendPy applies just enough pressure on a container to page out cold and unused pages that are not needed for nominal workload performance. It dynamically adapts to load peaks and drops, and so provides a working set profile for an application over time. As I mentioned earlier, detailed profiling data is collected in addition to cgroup stats and process-level stats. Facebook mainly relies on the jmalloc library for memory profiling and on eBPF capabilities in the Linux kernel for CPU profiling. We spent quite some time over the past couple of years to make sure that this data is available for smaller applications as well. Having this data aggregated and available across the entire fleet uncovers important optimization opportunities and help us to debug efficiency regressions and resolve some important bottlenecks. For instance, one of our important efforts right now is to identify and optimize libraries that are used by the majority of our infrastructure services. At our scale, even small optimizations applied to each library can result in significant efficiency wins for the entire infrastructure. So this set of tooling and methodologies creates a pipeline that at every step and at every level attempts to prevent or recover from resource usage regressions. This is how we prevent contention scenarios and allow our services and applications to run in clean environments with sufficient resources and deterministic failure conditions. In rare cases, when interactions between primary services and infrastructure services do become unsafe, cgroup controllers and unkiller are used to recover as quickly and safely as possible. It is important to notice that our resource guarantee is provided mainly by open source and publicly available software. For instance, our resource accounting is based on cgroups and systemd, and at the same time, memory accounting was improved using SandPy. Our key profiling infrastructure depends on BPF, eBPF, and gmalloc. The last but not least, our regression detection and prevention workflows can be generalized and applied to any fleet of Linux hosts running heavy compute workloads. Although our current infrastructure and operating model are rather reliable and effective, the Facebook's fleet keeps growing, providing us new opportunities and challenges. In addition to incremental improvements, there are three areas we would like to focus on moving forward. Our primary vision is to drive down the cost of infrastructure and free up more capacity for Facebook services to use. It is possible with elimination of bottlenecks, consolidation of similar applications, and deprecation of applications with a cost that cannot be justified anymore. At Facebook scale, even small optimizations applied to every host in our fleet can significantly impact Facebook's bottom line. Our efforts become increasingly important as Facebook continues to run hosts hotter with a single or multiple containerized workloads. Resources can be recognized and recovered with multiple techniques. We can either rely on the Facebook's job scheduler, which can use this additional capacity to run more tasks and jobs on the same number of hosts. Alternatively, many large services can use all the available resources on a host, and they typically rely on load balancing algorithms to recognize free capacity. So these services can handle more load on a fewer number of hosts when possible. Recognizing more capacity on each host is a way for Facebook to save money and power on future expansions. Our work on infrastructure software is not limited to efficiency and performance. Software reliability and standardization for widely distributed binaries have become a significant part of our responsibilities. For instance, monitoring reliability requires a new set of tools that we need to implement. All in all, there are many interesting opportunities ahead of us, and I'm very excited that we keep working on this problem. I hope you found this presentation very useful. Thank you for watching.